Hello, my name is Oliver Hazard. Speaking with me today is Sergio Cardona, and we are this year's ELECOMP Capstone team for Hexagon Manufacturing Intelligence. Our project is Part ID 2, part identification and post-processing using a collaborative robot. Our technical directors are Jonathan O'Hare, who is a business development manager at Hexagon and a URI alumnus, and Dr. Manbir Sodhi, who is a professor of industrials and systems engineering at URI.
As part of the team, you have myself, Sergio Cardona, a computer engineer with a minor in math, and Oliver Hazard, with majors in electrical engineering and Spanish. Let's talk about Hexagon. Hexagon is a global leader in quality control solutions for manufacturing, which one of its main goals is to turn manufacturing environment from automatization to autonomy.
One of the metrology devices that they make is this coordinate measuring machine, or CMM. The CMM consists of a gantry system that terminates in a probe tip supported by a granite base that moves in 6 degrees of freedom to determine if an object is in compliance with the company's specifications. However, the CMM process is very time consuming. Each test on the CMM can take as little as 30 seconds or as long as an hour. When you're measuring hundreds, if not thousands of parts, this time adds up. Additionally, the user is not immune from error. The CMM technician could load parts incorrectly, misidentify one part for another, or incorrectly document a serial number or unique identifier. If technicians do not spend their time operating the CMM, they can do more value-added work for the company. In the grand scheme, automating the CMM moves manufacturing towards Industry 4.0, which is a lights-out solution that is completely automated.
Our best anticipated outcome was to develop a part recognition system for inspection processes that recognizes unique identifiers. When developing this system, there were some key features that had to be taken into account. The different algorithms and interactions should be capable and easy to teach, added to an existing hardware, reliable, fast, and able to handle any errors. Our ABO was achieved. We documented and showed to our technical directors all the recommendations found for an ideal OCR environment. In addition to that, we developed a simple prototype of the system to prove the concept, using all the different parts that are needed for the system to be implemented. What were some important key technical accomplishments for our team? I'll list some of them. First, improved data collection method for object detection. Second, building of test apparatus and Cobot gripper. Third, creation of an OCR algorithm for reading UIDs. Fourth, determine best conditions for UID recognition with the OCR. And finally, and extremely important, was the proof of the concept of the complete Cobot process with the OCR. Now, let's talk about the economic impact for the company. When we talk about a system that is 99% successful at identifying train parts, it is possible to say that we contribute significantly to a labor cost reduction. Functionality will solve problems for our customers and they will recognize the value of the product.
This is a flowchart of the process we demonstrated was capable of being implemented. First, a drawer system near the CMM will be scanned to see if parts are loaded. If that is the case, the Cobot will then open the drawer and embed camera system will identify which parts are in the drawer. The Cobot, then using this information, will grab the part based on its optimal pick point. Then it will move the part to another camera based on nominal information of the location of that part's unique identifier. And from there, the camera will then do OCR optical character recognition on that part's unique identifier. Then the Cobot will move and repose the part for testing on the CMM. Once testing is completed, the part will be returned to where it's being held and the process will be repeated until there are no more parts to test.
During our project, we designed and built multiple tools for prototype and testing. Here are some pictures and a specification of the tools built. We created a test fixture that was used in multiple locations for OCR testing. We also created a clamp attachment They were used in place of the robotic two-finger gripper and some 3D models similar to the real parts provided in order to do the proof of concept. Our OCR algorithm was tested in different light environments using different size of characters, different pitch, yaw, and rotation angles in order to document all the information collected to finally send it to our technical directors in Hexagon. We did more testing. We also tested the minimum difference in RGB values between different UIDs and the background. We tested how our results change depending on the focus of our cameras. We also tested the minimum and maximum lux levels in a room and the recommended distance and angles from the camera to the parts. During all the testing, we found out that the pre-processing was extremely important when trying to recognize UIDs from different parts. Some of the pre-processing used in our test were a grayscale filter, an auto crop, which depends on the parts used to get a closer look to the UIDs and the resizing of pictures taken. Also, the system should have the ability to recognize multiple UIDs. Therefore, multiple algorithms should individually be written and put together to recognize bar and QR codes, machine dot matrices, and regular characters.
To be able to identify the parts, we first need to train a machine learning algorithm to recognize them. And to do that, we need to collect images of the parts. One method this was completed was by taking pictures of parts on a turntable. This is improved upon from last year's design. The turntable consists of a Raspberry Pi, which controls a stepper motor and cameras. As the stepper motor rotates, so does the table on which the parts are placed. Between rotations, pictures of the parts are collected. A new base was manufactured to allow for more parts to be in each image. Specifically, the base is now 17 inches diameter, and it was originally 10 inches. As well, a larger light box was created for the new base, but also to allow for better light diffusion and object clarity. Additionally, a multi-camera board was implemented to take pictures of parts at 3 different azimuth angles at the same time. As well, the lighting was controlled automatically by the Pi, and a new directory is created automatically each run. Another way images were collected was by laser scanning parts using the Hexagon roamer arm, and this was to allow for synthetic image generation from the STL files of these laser scannings. Having both methods to generate training data allows them both to be critically evaluated and to determine the optimal part identification strategy for Hexagon. Another Capstone team in the Industrials and System Engineering Department was in charge of the part identification aspect of the project, and they tested both real images and synthetic images. They also used 2 ways of identifying the parts: bounding boxes, which are the rectangles, and segmentation, which is represented with the highlights. They found that when training and testing with synthetic images, the algorithm was more successful. And this is then magnified when considering that a much larger quantity of synthetic images can be generated than real images. Additionally, the bounding box method was more accurate in all tests. Finally, the Cobot was implemented into the project. To simulate the Hexagon environment, a prototype cabinet system was made to hold a few parts, as well as a camera stand to act in place of the embedded OCR camera. An algorithm was generated in Polyscope, which is the native software for the Cobot, that takes initial input to determine which part to grab. Once the Cobot moves to the part, the gripper is tightened and moves to the camera. From there, the Cobot sends a signal to the Raspberry Pi, so it takes a picture of the UID and so that runs OCR on that picture. Once OCR is completed, the Raspberry Pi sends a signal to the Cobot to instruct it to continue. And the part is moved to an arbitrary spot that represents the CMM jig. From there, it would be the CMM process would be ran, but however, we don't have a CMM, so the Cobot then returns the part to its initial holding location. All points are given as variable values rather than fixed points, which means that given a new part, it'd be very simple to calculate the offsets needed to position the Cobot correctly. It is recommended that multiple OCR algorithms be made for different kinds of unique identifiers, specifically for QR codes, barcodes, dot matrices, and laser marked parts. These are unique categories we have recognized with different symbols and different lighting conditions that they need. As well, these algorithms need to be tested under more situations that are reflective of the real-world environment. It would increase the effectivity of the OCR algorithms to send the desired cropping of images of unique identifiers to the algorithm ahead of time. Finally, the system needs to be tested in the Hexagon environment rather than the prototype system we created.
Before we finish, we would like to thank our Technical Director, Jonathan O'Hare, Dr. Sodi, our Consulting Technical Director, Jeremy Peacock, and our Capstone Program Director, Dr. Sunak, for the continuous help and support during the entire project. Thank you.